Okay, I will share my screen. Share my screen and open this. Okay. Everybody can see my screen. You can hear my voice.
Yes, Doctor.
Okay, thank you for the response. Last week we stopped up to this slide, right? Can anybody give me a response about this? Last week I think we stopped here, right? Up to I think question number 5, if I'm not mistaken. Any response from you? Ada yang masih ingat lagi apa yang telah kita belajar? Betul Right, we stop here, right?
Betul, Doktor.
Okay, thank you for the response. Okay, so we have a few slides for this chapter 3. We have a few slides for this chapter 3. Wait, a few slides. Okay. So last week we have done this example 3.9, but I think up to number 5, right? Up to number 5. So we will continue for the rest of the questions. Okay. Maybe I will add more slides with there. I think better for me to add another slide so that I can further explain to you. Okay, so let's do this example 3.9. Okay, so an FM signal expressed as VFMT 1000 cos 2 pi times 10 power of 7t plus 0.5 sine 2 pi 10 power of 4t is measured in a 50 ohm antenna. Determine the following. Okay, so this is actually in the transmitter system. Okay, so the transmitter produces a VFMT, and this signal is supplied to the antenna, and the antenna will radiate the signal in terms of electromagnetic waves. Okay, and this 50 ohm is actually referring to the resistance in the antenna. Okay, resistance of the antenna. So the antenna receives the signal VFMT from the transmitter. It will radiate the signal in the form of electromagnetic waves. Okay. So when you get this kind of question, my suggestion is for you to straight away identify the related parameters. Okay. So identify the related parameters based on the given question. Okay, wait . So you are given 1000, so this is actually referring to VC, the peak amplitude of the carrier signal, and then you are given a 2 pi 10 power of 7. So if you divide with 2 pi, so you're gonna get 1 times 10 power of 7. Okay, so 1 times 10 power of 7 for the carrier frequency. Okay, you divide with 2 pi, so you're gonna get FC for the carrier. Okay, and then you are given 0.5, so this 0.5 is actually referring to the modulation index beta. Okay, and you are given another frequency which is 2 pi times 10 power of 4. So this is actually equal to, if you divide with 2 pi, you're gonna get 1 times 10 power of 4 hertz. Okay, which is referring to the modulating signal frequency, FM. Okay, and also you are given the parameter of R for the resistance of the antenna. Determine the following. Okay, so the first one asks you to find the unmodulated carrier power, okay, which is PC. So PC is equal to VC square divide with 2R. Okay, so this is actually equal to 1000 square divide with 2 times 50 ohm. Okay, so 1000 square divide with 100, so you're gonna get 10,000 watt. Okay, 10,000. Okay, so I suggest you to switch on your calculator and let's do the calculation together. Okay, so we get 10,000 watt of carrier power, and then the question asks about modulation index beta. So beta, we already obtained this parameter from the question, which is equal to 0.5. Okay, and then what? Peak frequency deviation. So this question asks you about delta F. Okay, asks you about delta F. So delta F is equal to beta multiplied with modulating signal frequency. Okay, which is equal to 0.5 multiplied with 10k, okay, 10 kilohertz. So this is equal to 5 kilohertz. Okay, so 10 kilohertz is from here 1 times 10 power of 4 from the question. Okay, from the question we get 1 times 10 power of 4, which is equal to 10 kilohertz. Okay, 10 kilohertz. So delta F frequency deviation is equal to 5 kilohertz. Okay, so if you don't understand, please ask me question, otherwise I move to the next question. Okay, then the question asks modulation sensitivity parameter. Find the modulation sensitivity parameter if you are given 200 millivolt to achieve part C. Okay, so what is this actually? Okay, so part C is actually this one. So you are given a voltage in order to achieve a delta F equal to 5 kilohertz. Okay, so now this is actually referring to the modulating signal peak amplitude Vm. Okay, because if you want to achieve part C, delta F, if you remember, delta F is equal to Kf Vm. Okay, so now you are given Vm in order to achieve delta F. Okay, so that means we want to find Kf actually. Okay, so Kf is equal to delta F divide with Vm. So this is 5 kilohertz divide with Vm is 200 millivolt. So how much is this? Okay, so 5k divide with 200 milli, so you're gonna get 25 kilo. Okay, so 25 kilohertz per volt. Okay, 25 kilohertz per volt. Okay, and then what? Draw the amplitude spectrum. Draw the amplitude spectrum. So how to draw the amplitude spectrum? So we know that beta is equal to 0.5. So if you want to draw the amplitude spectrum, that means we need to refer to the Bessel table so that we can get the number of spectrum and also the amplitudes. Okay. So 0.5. So if we maybe I draw here. Okay. So beta is equal to 0.5. So according to the Bessel table, if we flash back, let's go to the Bessel table. So 0.5 modulation index, we're gonna have a carrier and also 2 pairs of sideband. That means n is up to 2. Okay, number of significant sideband is equal to 2. Okay, 942403. Okay. Okay, so we already get the relative amplitudes, okay, which is 9424 and 03. Okay, so if you want to draw the spectrum, wait, I delete this one. So let's do a table. Okay, if we want to draw a spectrum, so we need to do the table. Okay, so J amplitude LSB and also the USB. Okay, so okay, so from here you can find the so 94, this is the amplitude. So we know that VC is equal to, the question is 1000. So 1000 volt. Okay, so V1 is equal to, so this is in terms of volt, so J1, so sorry, V0, J0 times VC, so this is equal to so 4 times 1000. Let's check. Wait. So I do like this. So V0 is actually equal to J0 multiplied with VC, so 0.94 multiplied with 1000. So you're gonna get 940. So this is the center frequency at FC. Okay, and then V1 is equal to 0.24 multiplied with 1000. So this is 240 volt. Okay, and then where's the location of the frequency? So the frequency is so we have 10 mega and for the carrier, and also 10 kilohertz for the modulating signal frequency. Okay, so this is 10 mega and here. Okay, so we know that FC is 10 megahertz. FM is equal to 10 kilohertz. Okay, so so the first one is FLSB. In FLSB is so 10 mega minus 10k. So this is FLSB. So F LSB F so this is equal to FC minus FM. Okay, so this is equal to 10 mega, 10 minus 0. Mega minus 10k. So this is 10 mega minus 10 kilohertz, 0.01, 9.99. So 9.99. Okay, megahertz, 9.99 megahertz, and then this is F USB 1 equal to 10 mega plus 10 kilohertz. So this is 10.01 mega. So this is, I think, megahertz. This is megahertz. Okay, 10.01. And then V2 is equal to 0.03 multiplied with 1000, so you're gonna get 30 volt. Okay, and then F LSB lower sideband 2, this is equal to 10 megahertz minus 20 kilohertz, 2 times FM, 2 FM. So this is 9.98. Okay, 9.98 megahertz. And then F USB 2 is equal to 10 megahertz plus 20 kilohertz. So you get 10.02. Okay, 10.02 megahertz. Okay, and if you want to draw the amplitude spectrum, okay, if you want to draw the amplitude spectrum, that means you need to draw amplitude versus frequency. Okay, so this is amplitude in terms of voltage versus frequency. We can use megahertz, for example. Okay, so the center here is the carrier center. Okay, so this is 10, for example, and then we have the first sideband is located at 10.01. okay, so here is 10.01. Over here is 9.99. okay, and the amplitude here is 240. This is 940. okay, so this is supposed to be lower. Okay, maybe I erase this one. Wait, so I make it lower over here. Okay, so 240. okay, and then another one here, so this is located at 9.98 megahertz and also 10.02 megahertz with the amplitude of 30 volt. Okay, 30. Okay, that's it. So this is the amplitude spectrum, amplitude volt versus frequency in megahertz. Okay, so if you don't understand, please ask question, otherwise we can move to the next question. Okay, so we have answered this. So the next asks about bandwidth 99% and approximate bandwidth by Carson's rule. Okay. So now we need to find bandwidth 99% and approximate bandwidth by Carson. So it is stated as 99%. Okay. So 99% of the bandwidth. So this question is quite strange, okay, because the question asks 99% of the bandwidth for both Carson's and also the Bessel, okay. Okay, so what we need to do now is to find the bandwidth by Bessel, okay. So bandwidth by Bessel is equal to 2 times n times Fm, okay. So we already know n, the number significant sideband is equal to ini 2 Why nobody correct me about this? Okay, the number of significant sideband is 2. Okay, according to the Bessel table. So I flashback again. So the number of significant sideband is equal to 2. Okay. Sorry, I make a mistake previously. So number of significant sideband is equal to 2. Okay. And then multiplied with the Fm. So this is equal to 2 times 2 multiplied with 10 kilohertz. So this is 40 kilohertz. Okay. And then bandwidth Bessel 99%. Okay, bandwidth Bessel 99% is equal to 99% of the Bessel bandwidth. Okay, so 99% of 40, how much? 0.99 times 40k, so 39.6. Okay, so 39.6 kilohertz. Okay, so this is bandwidth by Bessel. What about bandwidth by Carson? Is equal to 2 times delta F plus Fm. Okay, so this is equal to 2 times delta F. We already get from question number 3, which is 5 kilohertz plus 10 kilohertz. Okay, so 15 times 2, we're gonna get 30 kilohertz. Okay, so please correct me if I'm wrong in the calculation. Okay, tolong betulkan saya kalau saya ada buat careless mistake. Okay, so bandwidth Carson 99%. Carson 99% is equal to 99%.99 multiplied with 30 kilohertz. So this is equal to 0.99 times 30k. So 29.7. So 29.7 kilohertz. Okay, 29.7 kilohertz. Okay, so we already answer. So this is the answer, 99%. Okay. And then what? So we already answered this. So the next question asks you to find the power in the smallest sideband of the 99%. Now, what is this actually? So let's look from the this spectrum. If you see from this spectrum, maybe I can use a different color, for example green, for example. So if you see from here, Okay, so the this bandwidth, if you see from here, is actually 40 kilohertz. Okay, the total bandwidth from this amplitude spectrum is actually 40. So sorry about this. I erase this one. Is 40 kilohertz. 40. Okay, and according to the Bessel, okay, Bessel said that 99% of the Bessel, that means, so 99% is somewhere over here. Okay, which we get this around, sorry, we get this around 39.6. okay, so 39.6. So 39.6, if you see, if you go up, it consists of, okay, within the 39.6, it consists of the carrier component, it consists of the carrier component, okay, the carrier component, and also the first pair of sideband. Okay, within the 99% of the bandwidth, okay, if we cut, if you cut the total spectrum into 99% of the Bessel bandwidth, they're gonna be carrier component and the first pair of sideband, the first sideband. Okay, and if you see from here, within the 39.6 kilohertz of bandwidth, okay, the smallest component would be the first sideband. Okay, so within 39.6 kilohertz of bandwidth, the smallest component would be the first sideband. Okay, sideband yang nilai komponen yang paling kecil dalam 39.6 kilohertz of bandwidth ini adalah the first sideband, which is 240 volt of amplitude. Okay, so the question asks you to find the power in the smallest sideband of 99%. So this 99% change the way we measure the power. If, okay, if let's say there's no 99% over here, let's say that there's no 99%, for example, then the smallest would be the second sideband. Okay, so if we consider the whole bandwidth 40 kilohertz, okay, if we consider the whole bandwidth 40 kilohertz, that means the smallest sideband would be the second. But in this example, the question asks you to find the smallest sideband within the 99% of the Bessel bandwidth. So the smallest sideband would be the first sideband in this example. Okay, so therefore the smallest sideband here is P1. Okay, P1, which is equal to V1 square divided with 2R. So this is 240 square divided with 2 times, so R is 50 ohm. Okay, so this is equal to so 240 square divided with 100, so we're gonna get 576 watt. Okay, 576 watt. So this is the power of the smallest sideband in 99% of the bandwidth. Okay, again, if we consider even though we consider the Carson's bandwidth, for example, Okay, I use a different color with let's use what color? What else? Black, for example. Okay, so Carson 99%. Carson said that 99% would be 29. Okay, 29. So 29. This is wait, 10, 20, 29 is somewhere over here. So this is 20, 10 and 10, 20, so somewhere over here and also somewhere over here. So this is 29. See, this is 29 point. How much? 29.7 kilohertz. Okay. So within the first, within the 99% of Carson, we still get the smallest would be the first pair of sideband. Okay, so the first pair of sideband is the smallest sideband. Okay, the first sideband in this example. So you might wonder why this question asks you about 99%. Why? Okay, why? Okay. The issue is actually this is want to show you about the filtering process. Okay, because after the modulator, they're gonna be filtering process actually, where the filter will select only the desired bandwidth. Okay, and there's a long time ago, a few semesters ago, we have asked this kind of question in the final exam, where we give the we mention in the question that there's another bandpass filter which will select the bandwidth, a certain amount of bandwidth, and then calculate the total new power. Okay, I forgot the exact question. Okay, the question like this. At the beginning, the question asked you to find the total power. Okay, and then the next question said that if we put a bandpass filter which will select a certain amount of bandwidth, how much is the new total power? Okay, so if that kind of question, for example, if the bandpass filter, okay, let's relate with this question. Let's relate with this question. So if the bandpass filter select, for example, if the bandpass filter select a bandwidth 39.6, so 39.6 center at FC, center at carrier. Okay, so if let's say the bandpass filter select only 39.6, that means only this portion of bandwidth will be allowed to go through the filter. That means the new total power, okay, after we do the filtering process, will include three components, which is PC plus PLSB, the first sideband, plus PUSB. Okay, I just want to relate with the previous question. Okay, so that means sorry, so this is okay, so this is again PC. Okay, so this is 940 square divided with 2R plus 240 square 2R plus 240 square 2R. This is the case if you have a filter. Okay, the filter selects certain amount of bandwidth, and that portion will be allowed to go through the next process, and the total power would be reduced after we select only a portion of the bandwidth. Okay, So that is the thing about this 99%. So in my opinion, this 99% wants to relate with the filtering process. So the filter select only 99% and remove the others. So if within 99%, the total power would be up to the first sideband. The smallest power is at the first sideband, which is 576. Okay. Sorry. So we have answered this question, and then what? The next question asks you to find the total power. So what is this? The total power. The total power in this question asks you to find the PT, P total. So the question does not mention about 99%. It does not mention about anything. So this is actually the total power, and we have learned that the total power is actually equal to PC. Okay, the total power is actually equal to PC. Okay. So this is you can find the total power. Okay, you can find the total power. Wait, so the total power. Total power. So total power is. Okay. So P total is equal to PC. Of course, we know that. Okay. So let's say I want to use a different method. Okay, I want to use a different method. Let's do the long equation. Okay, let's do the long equation. So this is actually equal to where should I find? Maybe I need another. Wait. I need another slide. So let's add another slide so that I can use here. Okay. So P total is equal to J0 square PC plus 2 times J1 square PC plus J2 square PC. Okay. And here is J0 square is 0.94. PC, how much is PC? PC we already get PC 10,000. Okay, 10,000 watt. Okay, so 10,000. Okay, plus 2 times. Okay, so this is 0.24 square, 0.24 square times 10,000 plus 0.03, right? 0.03 square multiplied with 10,000. Okay, so this is how much? So 0.94 square times 10,000. So 836 plus 2 times 0.24 square times 10k plus 0.03 square times 10k. So 58585. Okay, so this is times 2 plus 8836. So we get 10,000, 10 6. Okay, so which is 10k. Okay, 10,006 or 10 kilowatt. Okay, so this is actually equal to PC. Okay, equal to PC. And another, there might be also a question. If the question asks you how much is the total information power, total information power. Okay, for example here, total so total information power means that the total sideband power. Okay, sideband power, because information contains within the sideband. So if the question asks you to find the total information power, it is actually referring to the total sideband power. Okay, because only the sideband carries the information. Okay, remember that. Okay, so if total information power, P total information, so this is equal to 2 times 0.24 square times 10,000 plus 0.03 square 10,000. Okay, so how much is this? So 0.24 square times 10k plus 0.03 square times 10k. So you're gonna get 5. This is 585. 585 times 2. So I get 1170 watt. Okay, so this is the total information power. Okay, so if you have question you can ask, otherwise I will move to the next slide. Okay, kalau ada soalan sila tanya. Okay, so we have answer up to number 8. Okay, we have answered up to number 8. Okay, so if you have question, please ask me. Okay, so we have gone through up to question number 8, and if there's no question, I will move to the next example. Okay, tak ada soalan so seems like there's no question. I hope that you understand. Okay, I hope that you understand. If you don't understand, please ask now. I can repeat again if you don't understand. Otherwise, we move forward. Example 3.110. 3.10. Okay. So example 3.10. Okay. An FM signal with 5 watt of carrier power is fluctuating at the rate of 10,000 times per second from 99.96 until 100.04 megahertz. Find a few parameters, A until E. Okay, so here it is said that the signal has a carrier power PC, okay, 5 watt, and it fluctuates, okay, fluctuates 10,000 times, okay, 10,000 times from 99.96 until 100.04. So if we draw the spectrum, let's say we draw the spectrum. So here is okay, so here is okay, so let's say that this is 99.96, this is 100.04. Okay, and it is said that the carrier fluctuates. Okay, sorry. Wait. Okay. So it is said that the carrier fluctuates. So the carrier fluctuates means moving, moving from 99.96 until 100.04 and then return until 99.96. So it moves 99 to 100, 99, 100, something like that. Dia berayun. It fluctuates from this within this range of frequencies. And the fluctuation rate is 10,000 times per second. So it moves within this range of frequencies 10,000 times in 1 second. Very fast. Okay. So if you see from here, from this picture, we can say that the center frequency would be Fc, okay, which is the rest frequency. Okay, 99.96 is the Fc minus delta F. 100.04 is actually equal to Fc plus delta F, and the center would be the rest frequency for the carrier. And then what? So what does 10,000 means? Okay, what does 10,000 means? So 10,000 means that it is referring to the modulating signal frequency. Okay, remember, only the input modulating signal will change the frequency of the carrier. So the frequency of the carrier change in accordance with the variation of the input. That means, okay, that means this 10,000 is actually referring to the modulating signal frequency, Fm. Okay, it is actually referring to the modulating signal frequency. Okay, because carrier signal fluctuates, carrier signal change the frequency in accordance with the input variation. So this input, which is 10,000 times, is referring to the frequency of the modulating signal. Okay, so find the first question. So the first question, find the carrier. Okay, so the carrier frequency is the center frequency, which is so carrier Fc is equal to how much is this? 100.04 plus 99.6 divide k to 100. So 99.96 megahertz plus 100.04 minus 99.96 divide with 2. Okay, so this is equal to 100 megahertz. Okay, okay, 100 megahertz. And then what? Carrier swing. Okay, carrier swing. So remember, the fluctuation here is actually referring to delta F and delta F. Okay, so the highest frequency here is Fc plus delta F. The lowest frequency here is Fc minus delta F. Okay, so now the question asks carrier swing. So carrier swing is equal to 2 delta f, which is equal to 100.04 megahertz minus 99.96 megahertz. So this is equal to 40 and 40, so you get 80 kilohertz. Okay, 80 kilohertz. So 40 above and 40 below. So 80 kilohertz. And then what? Find the frequency deviation. So frequency deviation delta f is equal to carrier swing divided with 2. So 80 kilohertz divide with 2, so we get 40 kilohertz of frequency deviation. Okay, and then what? Find the modulation index beta. So how to find the modulation index? So we know Fm. Okay, so modulation index beta f is equal to delta f over Fm, which is, this is 40 kilohertz divide with 10,000 times. So this is actually referring to the 10 kilohertz. Okay, so Fm, or the modulating signal frequency, is equal to the fluctuation rate, which is 10,000 per second or 10 kilohertz. Okay, so 10,000 per second means 10 kilohertz. Okay, it is referring to the frequency of the modulating signal. So modulating signal frequency is equal to the rate of fluctuation of the carrier. Okay, so this is equal to 4. Okay, and then what? Then the question asks you to find the power spectrum. Okay, so this is gonna take some time to draw. Okay, it's gonna take some time to draw because Bessel table for modulation index 4, the sideband will be 7. Okay, sideband would be 7. So okay, let's draw. Okay, so wait, I need more slide. So I will add one more slide here. Okay, or maybe 2 slides. Okay, so now we get what's the information? Beta f4. Okay, beta f4. How much is n? We already get PC. Sorry. So PC is equal to, given in the question, 5 watt. Okay, 5 watt. Okay, PC given in the question 5 watt. So how much? Okay, let's refer to the Bessel table. So here you see that n equal to 7. Okay, n equal to 7. Okay, so let's go back to the slide. So n equal to 7. Okay, okay, so n equals to 7. That means you're gonna have J0, J1, J2, J3, J4, J5, J6, J7. Okay, so okay, so now the question is ask you to find the power spectrum. That means we need to find power. Okay, power in terms of what? Okay, and then there's LSB and also the USB. Okay, so here power is J1, so J0 square PC, okay, which is equal to J0 square PC is equal, we don't know J0, so we need to find the value, okay, minus 0.4, wait, so I open another screen, so minus 0.4, so here minus 0.4, so correct me if I'm wrong, okay, minus 0.4, minus 0.07, okay, 0.36, 43, 0.43, 0.28, 0.13, 0.05, 0.02. Okay, so correct me if I'm wrong. Okay, so here is minus 0.4 square times 5. Okay, so minus 0.4 square times 5, so we're gonna get this equal to 0.8 watt. Okay, tak perlu letak, no need to use a W, so we understand that this is watt already in the header. Okay, so again this is J1 square PC, so this is equal to negative 0.07 square times 5. So this is how much? This is 0.0245. Okay, so 0.0245. Okay, and then 0.36 square, so J2 square PC, so this is 0.36 square times 5, 245, so this is J2 is 648. Okay, and then here is J3. So how much is this? This is 0.9245. Okay, 9245. J4 square PC, so this is equal to 0.28 square 5. So this is how much is this? 392. Okay, and then J5 square, J5, so this is 0.13 square 5. So this is 0.0845, 0.0845, and then J6 square PC. this is 0.05. So this is 0.0125, 0.0125 watt. And then so correct me if I'm wrong, so let's do together for this one. PC 0.02, so this is square, 0.2 squared. So this is 0.002, 0.002 watt. Okay, and then what? So let's find the frequency. So the first one is the carrier, so there's no upper and lower for the carrier because this is the center. And then so the frequency FM is 10k, center is 100 mega. Okay, center at 100 mega. Okay, so here is 100 mega, so this is, let's say, megahertz, frequency megahertz. Okay, so 100 mega minus 10 kilohertz, so this is 99, so 99.99 mega. So here is 100 mega plus 10k, so 100.01. okay, so here is 100 minus 100 megahertz minus 20k, this is 99.98. This is 100.02. okay, and here is 99.97. this is 100.03. this is 99.96, 100.04. this is 99.95, 100.05. So you can calculate, you can use 100 minus something something, so I just put the value here. So this is 99.94, 100.06, so this is 99.93, this is 100, okay, 100.07 megahertz. Okay, so now we need to draw. Okay, so when we want to draw power versus frequency, okay, so power here in watt. Okay, so let's say we're gonna have here, so there are too many. So here is, for example, center here 100, so 100.01. Okay, so this is so this is 100.01, 100.02. I don't know why this is 100.02. This is 100.03, 100.04, 0.05, 100, 0.06, 100, 0.07. Okay, and this is 99.99, 99, 99.97, 99, 99.96, 6. So the first one is 0.8. So 0.8 somewhere, you can say that 0.8 is somewhere here. Okay, and then here is 0.8, 0.025. Okay, 0.025. So here is very small. Okay, this here is 0.025. Okay, so this is 0.8. Here is 0.025, 0.025. Okay, and then 0.648. So I just estimate it's supposed to be a little higher. So here, okay, so somewhere here. Okay, so 0.648. Okay, and then 0.9245, 0.9245, so higher than the carrier. 9245. Okay, so 0.945. Okay, I just estimate that if it is higher, I need to draw it a little bit higher. Okay, we just do the estimation. So when you draw, you don't need to use ruler. Okay, don't use ruler. Okay, 0.392. So 0.392 is somewhere here. Zero point 0.0845. And then 0.0125. So 0.0125 here. And the last one, 0.002. So this is, remember, this is frequency in megahertz. Okay. Okay, so you can draw like this. Okay. Even in the final exam, if you draw like this, it's not good shape like this, but it is correct and it is labeled correctly, so you're gonna get full marks for this drawing. Okay, so don't use ruler, it's wasting a lot of time. Okay, make sure you draw correctly, the number of sidebands are correct, the number of power is correct, label is correct, so enough. Okay, so this is the power spectrum. So if you want to ask question, please ask question now. Otherwise, I will move to the next example. Okay. So we already answered this. Okay. Finish. Okay. Okay. So before we proceed, can I get your response? Are you still there, students?
Yes, sir.
Okay, thank you for the response. So if anybody wants to ask question, please ask now. Otherwise, I will move to the next slide. Okay, saya akan pergi kepada slide 3.11. Okay, 3.11 in an FM transmitter, the frequency is changing between 100 to 99.99 for about 4,000 times per second. The amplitude of the FM signal is 5 volt. So what is this actually? So the carrier frequency change between 100 to 99.98 for about 4,000 times per second. Okay, so if we draw the spectrum, okay, so this is, okay, so between 99.98 until 100, okay, so the fluctuations is about 4,000 times per second. Okay, and the amplitude of the FM signal is 5 volt. Okay, so this 5 volt is actually referring to the VC. Okay, and this 4,000 times of fluctuation rate is actually referring to the modulating signal frequency, FM. Okay, and if you estimate, if you see from here, you can estimate that the center here is the FC, okay, which is, if I do approximation 99.99 for the FC. Okay, kalau saya buat secara congak, saya nampak yang frekuensi tengah ini adalah 99.999. Okay, I do the estimation 99.99 center. Okay, so let's do the calculation. So number 1, find the carrier and modulating signal frequency. Okay, so we already know modulating signal frequency FM based on the fluctuation rate. Okay, FM is equal to 4,000 or 4 kilohertz. 4,000 hertz or 4,000 hertz or 4 kilohertz. Okay, and FC is equal to 99.98 megahertz plus half of it, 100 mega minus 99.98 megahertz divide with 2. Okay, so you're gonna get 99.99 megahertz. Okay, so this is the center frequency, and the distance is delta F and delta F. Okay, so number 2, carrier swing. So carrier swing is the maximum fluctuations, okay, maximum distance of fluctuations, which is equal to 100 mega minus 99.98 megahertz. So here is actually equal to 2, which is 20 kilohertz. Okay, 20 kilohertz. Okay, 20 kilohertz. And then what? Find the amplitude spectrum. How to find this? So we know how much is we know FM, we know FC, we know delta F. We can find beta actually. So from here, actually we can find delta F. Okay, delta F is equal to 20k carrier swing divide with 2. So we're gonna get 10 kilohertz of delta F, frequency deviation. Okay, and then we can find the modulation index beta F is equal to delta F divide with Fm. So this is equal to 10 kilo divide with 4 kilohertz. Okay, so you're gonna get this 2.5. Okay, 10 divide with 4, you're gonna get 2.5. Okay, so 2.5 according to the Bessel table, you're gonna get up to 5 pairs of sideband, or the number of significant sideband is equal to 5. Okay, so again we need to draw the table. Okay, so I will show you. Okay, I will show you how to draw. So I will add another slide over here. Okay, and we can do the drawing over here. So okay, beta f 2.5, so beta f equal to 2.5. Number of significant sideband equal to 5 according to the Bessel table. Okay, so we need to draw the amplitude spectrum. Okay, that means we know the VC is 5 volt. Okay, so VC is equal to 5 volt according to the question. So now we can draw so this is LSB megahertz. We can do here USB megahertz. Okay, so here J0, J1, J2, J3, J4, J5. Okay, so here is 0.4, 0.5. So J0 is negative 0.05, negative 0.05. J1 0.5, 0.45. So this is 0.45. J3 is 0.22, 0.07, 0.02. So amplitude here is equal to V0 is equal to negative 0.05 multiplied with 5. So you're gonna get negative 0.25, negative 0.25. So here, and then V1 is equal to 0.5 multiplied with 5. So you're gonna get here is 2.5. So this is voltage. And then V2 here is equal to so V2 here is equal to 0.45. So this is 2.25, 2.25. V3 here is equal 0.22 times 5. So this is 1.1. And then V4 here is 0.07 times 5. So here is 0.35 volt. And then here is V5. So here is V5 is equal 0.02 times 5 equal to 0.1 volt. Okay, and then what about the frequency? Okay, frequency here Fm is 4K and then Fc is 99.9. Okay, so Fc is given as 99.99 megahertz. Fm is equal to 4 kilohertz. Okay, so therefore here is Fc minus Fm, which is equal to how much? 99.99986. 99.99986. Okay, so here is 99.986. Over here is 99.994. Fc plus F. Okay, you can cross check my answer. Please cross check my answer. Fc plus Fm. So this is 99.994. Okay, 99.994 megahertz. And then Fc minus 2 Fm. Okay, so this is 99.982 megahertz. Fc plus 2 Fm, so this is 99.998 megahertz. Fc minus 3 Fm, so this is 99.978 megahertz. Fc plus 3 Fm, which is plus another 4, so it is 100.002 megahertz. And then Fc minus 4 Fm, which is 99.974. Okay, 974. So this is Fc plus 4 Fm, so this is 100.006. Okay, and then Fc minus 5 Fm, so this is 99.970 megahertz. And here Fc plus 5 Fm, so this is 100.010 megahertz. Okay, and then from here we can do the drawing. Okay, for amplitude versus frequency. Okay, so the first one is minus 0.25. Let's say somewhere here. Okay, minus 0.25. This is at 99. So this is megahertz. Okay, F megahertz, and then here 99 something. Okay, so we get here is at 99.994. This is 99.986. Here is 99.9. here is 99.982. Over here is 100.002, so 100.002. So here is 99.978, 99, and then 99.974, 99.974. Here is 100.006. 100.010. Okay, here is 99.970, so 99.970. Okay, so when you want to draw, the first sideband is 2.5, 2.5, okay, so 2.5 somewhere here, 2.5. So you see, even if I'm not using ruler, it's going to take some time to draw this, 2.5. So you need to practice so that you know how to draw. So 2.5 and then 2.25. And then 1.1. But here is 1.1, and then 0.35. And then 0.1. Okay, finish. So this is the amplitude spectrum. Okay, this is the amplitude spectrum. So make sure you practice use how to draw this one. Okay, so we already answer amplitude spectrum like this. Okay, and then bandwidth. The question asks to find the bandwidth using Bessel and Carson's rule. Okay, so bandwidth by Bessel is equal to 2 times n times Fm. So this is 2 times 5 times 4 kilohertz. So 10, so this is 40. Okay, and then bandwidth by Carson, this is 2 times delta F plus Fm. So this is equal to 2 times delta F10 plus 4 kilohertz. So this is equal 14 times 2, so 28 kilohertz. Okay. Finish. And then question number 5. So question number 5, find the average power at the transmitter if the modulator carrier power is 5 watt. Okay, so now it said that the carrier power is 5 watt. Okay, and we need to find so the carrier power is 5 watt. So how much is the average power at the transmitter if the modulator carrier, so the modulator producer carrier power of 5 watt. So we need to know how much is the total power. Okay, so let me erase some of this content. Let me erase this one. Yeah. Oh, sorry, cannot be erased. Okay, so let's do so again, no place to write. Okay, so where should I erase? So okay, wait there. Okay, so within the transmitter, okay, this is the transmitter, for example. So the modulator, okay, the modulator, for example, for example, the modulator is over here, for example, okay, somewhere here. So the modulator produces a carrier power of 5 watt. We can find the total power, P total, produced by the transmitter. Okay, so the question says that the average power, it is actually referring to the remaining power produced by the transmitter. Okay, the average power in the transmitter excluding the carrier power produced by the modulator, which is 5 watt. So we need to find the total power first. P total is equal to Vc square divided with 2R. So how much is Vc? So Vc is 5 volt. Okay, 5 volt square divide with 2 times R. So R is not given in the question. R is not given in the question. So assume that R is equal to 1. Okay, let's assume R equal to 1. Okay, so the question is supposed to give you the R values. So assume that R equal to 1. Okay, so this is 25. So this is 12.5 watt. The total power is 12.5 watt. Total power produced by the transmitter, which is transmitted to the antenna. Okay, but now we know that the carrier power or the modulator power produced by the modulator is 5 watt. So how much is the average remaining power within the transmitter? So therefore we can write that P transmitter, okay, so P transmitter, which is the remaining power in the transmitter, is equal to P total minus P modulator. P modulator is the carrier power produced by the modulator, which is stated in the question. Okay, modulator carrier power 5 watt. Okay, so 12.5 minus 5 watt. Okay, so we get here 7.5. Okay, this is 7.5 watt. Okay, so 7.5 watt is actually referring to the rest of the power produced by the transmitter. Okay, so the modulator produced 5 watt, and the total power, we know that 12.5 total power is the power transmit to the antenna. Okay, so therefore the average transmitter power is equal to total power minus the modulator power, which is 7.5 watt. Okay, so if you have question, please ask. Otherwise I will move to the next question. Okay, So if you see that this example 3.11, we already answer up to question number 5. Now we want to move to the next topic, which is pre-emphasis and de-emphasis. Okay. Pre-emphasis and de-emphasis. What is this actually? So before we move forward, can I get your response? Are you still there, students?
Yes, sir.
Okay, thank you for the response. So if you want to ask question, you can ask this question. Okay, boleh tanya. Sesiapa nak tanya soalan, silakan tanya. If you don't ask question, I will assume that you understand how to answer the question. Okay, kalau tak ada soalan, saya anggap semua faham ya. Okay. Okay. So pre-emphasis and de-emphasis. So what is this actually? Okay. So FM signal has a non-uniform distribution of noise. The noise at higher modulating signal is higher in amplitudes compared to the noise at lower frequencies. So that means if we use a higher modulating signal frequency, the noise produced by the system will be higher in terms of amplitudes. Okay, so information signal with uniform amplitude will produce a non-uniform SNR at the output. Okay, so higher modulating signal frequency have lower SNR compared to the lower frequency of modulating signal. So what happened actually? So in order to compensate this, we need to boost the amplitude. Okay, so let's see that the last statement here. Okay, we say that if we want to compensate the noise, which we want to increase the SNR actually, we need to boost the amplitude. We need to increase the amplitude of higher frequency modulating signal before the modulation process, and this is what we call as a pre-emphasis. So in this is happen at the transmitter, while at the receiver side we can reduce. Okay, we can reduce the amplitude with the same amount of that we have done in the transmitter. So we increase at the transmitter and we reduce at the receiver. Okay, so we reduce or we attenuate the amplitude of the signal, which is what we call as the de-emphasis after the demodulation process. So this will improve the SNR. So the situation looks in picture A. So let's see the situation here is like this. So you see that this is the center here is the carrier frequency. Okay, and this is a uniform FM signal. Remember, FM signal does not change the amplitude of the carrier. The amplitude of the carrier remains the same. While you see that here, if let's say we use a higher value of FM, so if we go to the right and left side, okay, so the right and left side is the fluctuations. Okay, the fluctuations of the carrier signal. Okay, and you see that if we use a higher value of FM modulating signal, okay, the noise level, so the blue color here is the noise level. So the noise level will increase as we use the higher value of modulating signal frequency. Okay, you see that the noise level is higher. This is a theoretical concept. The higher the modulating signal frequency that we use, the higher would be the noise level. Okay, so what happens if the noise level is higher? What happens? What happens is that the SNR will be reduced. You see that if we use the lower modulating signal frequency, the SNR is higher compared to the SNR if we use a higher value of modulating signal frequency. Okay, so this is not good for the output signal, because what we want is we want the SNR to be as high as possible. Okay, so what can we do actually? Okay, so we want the SNR to be as high as possible. Okay, so what we need to do is we need to increase the input signal level. Okay, we need to increase the input signal level when we use a higher value of modulating frequency. Okay, so we need to increase the value of input signal, which is we need to increase the Vm actually. We need to increase the Vm so that at higher modulating signal frequency, we're gonna get higher value of amplitude, so that the SNR would be uniform. Okay, so that the SNR would be increased actually, compared without increasing the amplitude. Okay, so we increase the amplitude of the input signal so that we can produce a better SNR at the output. And if you see from here, at lower value of Fm for the SNR compared to the higher value of modulating signal frequency, so we can get the higher SNR compared to the previously. So this is what we call as the pre-emphasis and de-emphasis. Okay, we want to achieve a higher SNR value. Okay, so if you want to see the example of this, here is the example from the Wayne Thomas's book about the pre-emphasis and de-emphasis. Okay, remember pre-emphasis and de-emphasis. Pre-emphasis, we increase the amplitude of the input signal, okay, at the transmitter. That's what we call as a pre-emphasis. Pre-amp, okay, we increase. De-emphasis, de-amp means that we reduce the amplitude of the carrier, the amplitude of the signal after the demodulation at the receiver. Okay, so we increase, for example, if I increase 10 volt, I multiply it with 10 volt in the transmitter, I need to reduce 10 volt at the receiver. So it needs to be balanced. So when I increase at the transmitter, I need to reduce at the receiver to become balanced. Okay, apabila kita naikkan amplitude pada transmitter, kita juga perlu menurunkannya pada kadar yang sama pada receiver supaya balance. Okay, so let's look at the example so that you can have more understanding about this situation. So given a direct FM frequency modulator VCO with a deviation sensitivity K1 equal to 1 kHz per volt. Okay, a PLL phase locked loop FM demodulator with a transfer function of KD 1 volt per kHz and the following input signals. So you are given 3 input signals, okay, at 3 different frequencies: 1 kHz 4 volt, 2 kHz 2 volt, and 3 kHz 1 volt. Okay, so now you are given a transmitter and receiver. So the VCO is located at transmitter, the PLL is located at the receiver side. Okay, and you have 3 frequencies of input with 3 different amplitudes. Okay, determine the first question. Determine the frequency deviation, which is delta F, at the output of the VCO in the transmitter for the 3 input signal. Okay, and then what? And the demodulated voltage at the output of the PLL demodulator. And then what? Question number 2, you are given noise values generated by the system, which is 1 kHz. At 1 kHz frequency, the noise is 0.1 volt. At 2 kilohertz, the noise is 0.25 volt. At 3 kilohertz, the noise is 0.5 volt. Find the SNR. Okay, so I will show you the picture for question number 1 and 2. Okay, so question number 1 and 2 is referring to the picture on the left. Okay, so you are given VCO, you are given PLL, phase lock loop. Okay, phase lock loop at the receiver. Okay, so we have transmitter and receiver. You are given input input signal with 3 different frequencies. Okay, so this VCO has a transfer function of K1 1 kilohertz per volt. That means if you want to produce hertz at the output, you need to multiply with the voltage. Then you can get the frequency. Okay, so now we want to find the frequency deviation at the output of the VCO, which is equal to amplitude multiplied with the K1. Okay, so delta F1 is equal to VM1 multiplied with K1. So 4 volt multiplied with 1 kilohertz, so we get 4 kilohertz delta F. And then for the second frequency, the amplitude VM2 is 2 volt multiplied with K1, so we get 2 kilohertz. And then the third frequency is the amplitude is 1 volt multiplied with K1, 1 kilohertz, so we get 1 kilohertz. Okay, so this is transferred to the receiver. It goes to the phase locked loop demodulator. Okay, so we have 3 delta F, delta F1, delta F2, delta F3. Okay, remember question number 1 and question number 2 is without pre-emphasis and de-emphasis, so we want to compare later. Okay, and then what? At the phase locked loop, okay, since we have a delta F1, delta F2, delta F3, okay, so we want to produce V out. Okay, so V out is equal to so we need to multiply it with KD. So if you want to get voltage, we need to multiply it with frequencies. Okay, so V out 1 is equal to delta F1 multiplied with KD. So 4 kilohertz 4 kilohertz of delta F1 multiplied with 1 volt per kilohertz, so we get 4 volt. And then at V out 2 is delta F2 2 kilohertz multiplied with KD 1 volt per kilohertz, so we get 2 volt. And then V out 3 is delta F3 multiplied with KD, so we get 1 volt. Okay, and if we draw the frequency spectrum for the output of the PLL, it would be like this. So at 1 kilohertz 4 volt, 2 kilohertz 2 volt, 3 kilohertz 1 volt. Okay, and this is similar with the input. Of course, we want to produce output similar to the input. Okay, so the question number 1 asks you to draw the to find the delta F, to find the V out, and you can draw the spectrum. Question number 2, it gives you the noise level. Okay, question number 2 gives you the noise level, which is 0.1 volt at 1 kilohertz, 0.25 volt at 2 kilohertz, and 0.5 volt at 3 kilohertz. So this is the noise. We can say that this is Vn. Okay, so you see that here SNR, signal level over noise level. So when we want to calculate the SNR would be for the SNR at 1 kilohertz is equal to 4 divide with 0.1, so we get 40. 2 divided with 0.25, we get 8 at 2 kilohertz. SNR at 3 kilohertz, we're going to get 1 volt divided with 0.5, so we get 2. Okay, so SNR equal to 40 at 1 kilohertz, SNR equal to 8 at 2 kilohertz, SNR equal to 2 at 3 kilohertz. So you see that the SNR becomes smaller as we increase the modulating signal frequencies. Okay, so we have a 3 FM, FM1, FM2, and FM3. So the SNR becomes smaller if we increase the value of modulating signal frequency. Okay, so now how can we improve this situation? So the third question, okay, the third question here said that determine the frequency spectrum at the output of the pre-emphasis network. The frequency deviation at the output of modulator output, the demodulator output voltage, the frequency spectrums, and SNR at the output of PLL demodulator and at the output of de-emphasis network. So now we introduce pre-emphasis and de-emphasis. We repeat the process of number 1 and number 2. So now we want to see what happens if we put pre-emphasis and de-emphasis in the system. Okay, so you see that pre-emphasis, we put pre-emphasis before the modulation process at the transmitter. Then we transmit the signal to the VCO. And then at the receiver side, we introduce de-emphasis network after the demodulation process at the PLL. Remember, when we increase the amplitude at the transmitter, we need to reduce the amplitude with the same amount at the receiver. So it becomes balanced. We increase, we decrease. Increase and decrease, so balance. So what happened now? You see that we have the input as before, 4 volt at 1 kilohertz, 2 volt at 2 kilohertz, and 1 volt at 3 kilohertz. Okay, and it will go to the pre-emphasis network. Pre-emphasis will increase the amplitude. So what happened is that here the multiplication is times 1, this is times 2, this is times 4. Okay, so 4 volt multiplied with 1, 2 volt multiplied with 2, and 1 volt multiplied with 4. Okay, so this is not given in the question about the multiplication rate. Okay, so this example wants to show you that pre-emphasis increase the amplitude for the higher value of modulating signal. Okay, and then it puts inside the VCO. So at the VCO, we're gonna get the frequency deviation delta F, delta F1, delta F2, delta F3. Okay, so delta F is equal to VM1 multiplied with K1, we get 4 kilohertz. Delta F2 is 4 volt multiplied with 1 kilohertz, K1, and then delta F3 also, we get 4 volt multiplied with 1 kilohertz, so we get 4 kilohertz for the delta F, delta F1, 2, and 3. And then it goes to the PLL with a transfer function of 1 volt per kilohertz. So we're going to get the V out. V out is equal to delta F multiplied with KD. Okay, so delta F multiplied with KD, so we get 4 volt, similar with V out 2 and V out 3, 4 volt. Okay, and you see that from here the PLL introduces a noise, which is as in the previous picture A. So the noise is given as before, similar like before, 0.1, 0.25, and 0.5. And from here we can calculate the SNR. Okay, which is SNR for SNR at 1 kilohertz, it is 4 divided with 0.1, so we get 40. SNR at 2 kilohertz, 4 divided with 0.25, so we get 16. At 3 kilohertz, the SNR is 4 divided with 0.5, so we get 8. Okay, so you see that the SNR is better than before. 40, 16 and 8 compared to previously 40, 8 and 2. Okay, so this is not finished yet, because we need to supply the signal to the de-emphasis. We need to reduce the amplitude with the same amount like we increase at the transmitter. So times 1, times 2 and times 4, we need to reduce divide 1, divide 2 and divide 4. Okay, so here 4 volt, from 4 volt we divide with 1, so we get 4 volt, and then 4 volt divide with 2, we're gonna get 2 volt. 4 volt divide with 1, sorry, 4 volt divide with 4, so we're gonna get 1 volt. Okay, we decrease with the same rate like we increased previously in the transmitter. Similar with the noise, so if we de-emphasis also will reduce the noise level with the same rate. Okay, so 0.1 divide with 1, so we get 0.1, same. 0.25 divide with 2, so we're gonna get 0.125. 0.5 divide with 4, so we're gonna get 0.125. So both signal level and noise level is reduced with the same rate, same values. Okay, and still we're gonna get the same SNR. Okay, so 4 divide with 0.1, we get 40 SNR at 1 kilo. 2 divide with 0.125, we're gonna get 16 at 2 kilohertz. And 1 divide with 0.125, we're gonna get 8 as SNR equal to 8 at 3 kilohertz. So if you compare, okay, the pre-emphasis and de-emphasis produce better SNR, especially for the higher value of modulating signal frequency. Okay, so this is the reason why the FM transmitter and receiver use the pre-emphasis and de-emphasis process. Okay, so this is okay, so I move forward. I move to the next slide, which is about the FM signal generation. Okay, FM signal generation. So how to generate the FM signal? So we have two methods. The first one is to use a direct FM modulator. Okay, that means we are directly change the frequency of the carrier in accordance with the amplitude variation of the input signal. Okay, so direct FM means that we are directly change the frequency of the carrier. So there are many direct FM modulator types in the real world. Okay, one of it is what we call as a varactor diode. Okay, so the varactor diode change by the model. So here the varactor diode, you see that the varactor diode, the input signal here is a modulating signal, which is a VMT over here, VMT. Okay, and then we have here we have capacitor, we have R1 and R2. Okay, we have a crystal control oscillator over here, which control the input to the base of the transistor. And remember how transistor works is that when the base of the transistor more than the threshold value, current can flow from collector to the emitter. Otherwise, it will switch off. Okay, and if you see that the crystal control oscillator frequencies change in accordance with the KF VMT. Okay, see that the oscillator frequency is changed by the modulating signal amplitude. So crystal control oscillator frequency change FC plus KF VMT. Okay, so for example, like the varactor diode, the external modulating signal voltage adds to and subtract from the DC bias developed from the R1 and R2, okay, which change the capacitance of VD1 is here, and frequency of oscillation by the oscillator, crystal control oscillator. Okay, so the voltage changes of VMT change the frequency of the carrier, directly change the frequency of the carrier. So positive alteration of the input modulating signal increase the reverse bias at VD1, okay, and increase the frequency oscillation. So during the positive alterations, it will increase the frequency oscillation from FC plus delta F. Okay, so positive alteration of the modulating signal will produce FC until FC plus delta F maximum. And then negative alteration of the input modulating signal will decrease the carrier frequency until FC minus delta F. Okay, so the process that you see here is that the components inside the modulator directly change the carrier frequency in accordance with the amplitude variation of the input modulating signal. Okay, so that's why the name is direct. Okay, in this case, actually we are indirectly change the phase of the carrier actually. Okay, sebenarnya if we do the direct FM, we are actually do the indirect phase modulation. Okay, indirectly we are actually changing the phase of the carrier, okay, in this process. Okay, and we're gonna see the second type of FM signal generator is what we call as the indirect FM. So indirect FM means that we are indirectly change the frequency of the carrier, and we are actually directly change the phase of the carrier. Okay, so kalau kita secara tak langsung menukar frekuensi carrier, sebenarnya kita secara langsung menukar fasa carrier. Okay, remember, frequency and phase are related to each other. Okay, so how to generate the indirect FM? Okay, so FM and PM are interrelated. As I mentioned, it cannot be changed without one another changing. So the information signal frequency also deviates the carrier frequency in PM. So if we change the phase of the carrier, we are indirectly change the frequency of the carrier. Okay, if we directly change the phase of the carrier, we are indirectly change the frequency of the carrier. Okay, so phase modulation produce frequency modulation. So in this case, we are actually do the phase modulation process. Okay, so we are producing FM through the PM process. Okay, we are producing frequency modulation through the process of phase modulation. Okay, kita menghasilkan frequency modulation melalui proses phase modulation. Okay, so how to do this? First, the information signal is integrated. Okay, integrated, khamirkan, and then used to phase modulate. We use a phase modulation with a crystal control oscillator, which provides frequency stability. So we mix, we multiply the the signal with the oscillator frequency. Okay, and we're gonna produce narrowband FM signal. Okay, so in order to minimize the distortion in the phase modulator, the modulation index is kept small, thereby resulting in narrowband FM. So what we will produce is actually narrowband FM signal. Okay, we do the process of phase modulation, we are actually produce the narrowband FM. Okay, so the narrowband FM, okay, remember that it is firstly integrated, this one. So this is the integrate process of the input modulating signal, and then we multiplied with the carrier signal to produce a narrowband FM. Okay, the narrowband FM signal is multiplied in frequency by means of frequency multiplier to produce a wideband. So if we want to produce wideband, we need to use a multiplier. The frequency multiplier is used to perform narrowband and wideband conversion. So I will show you about this. The frequency deviation of this new waveform is m times that the old. Okay, so we're going to see this example, which is this one. Okay, and this is very important for your final exam, so you need to understand about this process. Okay, so if you see from here, the above picture is actually referring to the picture below. Okay, so this is, if I draw this one, okay, so this picture here, the one that I circle red color here, is actually referring to the picture below, which is the narrowband phase modulator. Okay, so this is the narrowband a block diagram of the indirect FM generation, okay, which is referring to the picture below. Okay, and you see that this frequency multiplier is actually over here. Frequency multiplier is actually over here. Okay, again, this is you need to understand about the equations involved in this process. Okay, so you see that here the VCT, so VCT here is given as, okay, VCT is given here is as, you see that here is actually VC cos 2 pi FCT. Okay, and then here you see that MT here is the input message. Okay, so MT, where should I write? So VMT is given here is actually is equal to VM cos 2 pi FMT. Okay, so this is a VMT actually, VMT. Okay, and a 90-degree phase shift cos becomes sine function, so it becomes here VC sine 2 pi FCT. Okay, and then what? So this input here to the integrator, remember that first we need to do the integration process. So this is the input here is 2 pi kf Vm cos 2 pi Fmt. Okay, and if we do the integration of cos, we're gonna get sine. Okay, so we're gonna produce here, so we're gonna produce this one, so 2 pi kf 2 pi kf Vm sine 2 pi Fmt divide with 2 pi Fm 2 pi Fm. Okay, and if you see from here, we can cancel out 2 pi, okay, it becomes kf Vm over Fm, okay. So kf Vm over Fm is actually beta f sine 2 pi Fm t, okay. So beta f sine 2 pi Fm t is insert into the balance, this one, narrow band phase modulator, this one, so this is this part here is what we call as a balance modulator, okay. It will do the process of multiplication, okay. It will do the multiplication process. So this is the balance modulator, or what we call as a narrow band phase modulator, okay. It will do the multiplication. So what happened here at, for example, here at point A, for example, okay, at point A, it is equal to Vc Vc sine 2 pi Fct multiplied with beta, so multiplied with beta sine 2 pi Mt, okay. So this is sine and sine, so Vc beta, so I rearrange, so this is Vc beta f, sorry. Please try to understand this, this is important for your final exam, okay. So sine and sine, we can make it as cos minus cos, okay. So this is equal to Vc beta f over 2, Vc beta f over 2 in bracket cos 2 pi Fc minus Fm sine and sine, okay. So this is a lower sideband, okay, sorry. So this is a lower sideband minus cos, so I make it here cos 2 pi, so this is t, Fc plus Fm t, close bracket, okay. So sine and sine, we're going to produce a upper sideband and also the lower sideband, okay. And then over here, down here is VCT, so here is Vc, because Vc is supplied here, Vc cos, Vc cos 2 pi Fct, okay. So this is at point B, for example. And then what? At point C, okay. So at point C, we need to plus A and B, okay. At point C, it is plus A and B. So maybe I will draw, where should I put here? Maybe I can put here, okay. So at point C, okay, at point C, it becomes Vc cos 2 pi Fct plus, okay, Vc beta f over 2 lower sideband cos 2 pi Fc minus Fmt minus Vc beta f over 2 cos 2 pi upper sideband Fc plus Fm t. Okay, so this is like the amplitude modulation actually. Okay, so narrowband FM is similar with the amplitude modulation, double sideband full carrier. Okay, and if you want to draw the spectrum, okay, I will show you the spectrum. Okay, so for example, here is amplitude versus frequency. So here is the center here, Fc, with the amplitude of Vc. Amplitude is Vc, and you have here the upper and lower sideband. Here is Fc plus Fm, Fc minus Fm. Both of these has the amplitude of Vc beta f over 2. So Vc beta f over 2. Okay, so Vc beta f. Okay. What about the bandwidth? The bandwidth would be equal to Fm. Okay. What about the power? So the power would be so power, when we want to calculate the power, so P total is equal to PC plus P LSB plus P USB. Okay, so this is Vc square over 2R plus LSB is Vc beta f. So that means Vc beta f over 2 square divide with 2R. Okay, plus Vc beta f square. So we get the total power. Simple as that. Okay, so you need to know about this in order to produce what is the output frequency equations. So given the input, so find the output equations. Okay, so actually from the output equations you can draw the frequency spectrum, you can find the bandwidth, you can calculate the power. Okay, anybody want to ask question about this? Do you understand? You want me to repeat or what? Ada soalan nak tanya? So this actually I explained to you up to this the output here. Okay, so up to this is narrowband FM. So we get the narrowband FM FM signal. So if you want to produce a wideband FM, we need to use a frequency multiplier to increase the frequency from low frequency to higher frequency. That one is what we call as the frequency up conversion. Okay, so frequency up conversion, there are two types. Okay, there are two methods to increase the frequency, where we want to convert a narrowband FM to become wideband FM. Okay, so first we can do the heterodyning process. Heterodyning means we mix two signal to produce upper and lower frequency. So that upper frequency is the up conversions. We can take that upper sideband as a up conversion frequency. Okay, so heterodyning means heterodyne, mixing. You mix two signal. Remember, when we mix two signal, we do the multiplication process in time domain. We're gonna produce upper and lower sidebands. So we're gonna take the upper sideband for the up conversion frequency. Okay, and then multiplication. Multiplication means that we supply the input to the frequency multiplier to increase the frequency of the input. So if the input is, for example, 10 kilohertz, we increase by 10 times. That means 10 kilohertz multiplied with 10, so the output of frequency multiplier is 100 kilohertz, something like that. Okay, so we're gonna see the picture over here to understand about these two processes, heterodyning and also the multiplications. Okay, so let's look at this picture. Picture A on the left side is the heterodyning method. Picture on the right is the multiplication process. Okay, so what's the difference actually? Okay, so let's see the difference. Okay, so assuming that here is the input, you see that these are the modulation parameters. We have the carrier, input carrier, delta F input, modulation index. M here is the modulation index, Fm is the modulating frequency, B here is the bandwidth. Okay, so what happened in the if we put additional balance modulator? So if we want to do this process, that means we change this frequency multiplier into the heterodyning process. Okay, so this is, we put this after the narrowband phase modulator. We put the another balance modulator. We put so here, over here is from the narrowband and BFM. Okay, put inside another balance modulator to produce the up conversion in frequencies. Okay, so what happened in the balance modulator? We mix the signal with oscillator, RF oscillator, with the frequency of FRF. Okay, remember, when we do the multiplications, we're going to produce upper and lower sideband. Okay, so here we're going to produce, here is FC plus FRF and also FC minus FRF. Okay, balance modulator use the process of multiplication. Remember the X symbol. Okay, so it will produce 2. Okay, and then this band pass filter will select the sum frequency. That means we're gonna select only FC plus FRF. Okay, what about other parameters? So other parameters does not change in this process. Delta F out same as delta F in. VMT out equal to VMT in, modulating signal. This one is, sorry, M here is sorry, this M here is actually beta. Ini sebenarnya beta. Okay, M here is beta. Okay, so beta, this is from different books, so that's why some other literature books use M. Okay, so M here is beta. Okay, and then here is the modulating signal frequency remains the same. Bandwidth also remains the same. Output, okay, same as input. Okay, so you see that in heterodyning process, only the carrier frequency will change. The other modulation parameter does not change. Okay, so this is using the heterodyning method. Okay, what about if we use a multiplication method? Okay, So input here is a narrowband FM. Okay, so this multiplier has a multiplier factor of n. What happened to the output? Okay, so carrier frequency will change. So FC out is equal to n times FC in. Okay, delta F out equal to n times delta F in. Modulation index beta is equal to n times modulation index. Modulating signal frequency FM remains the same. Bandwidth would be bigger. Why bandwidth is not n times beta? Why? Why the bandwidth is not bandwidth out equal to n times bandwidth in? Why? Because it is depending on the value of beta. Okay, we need to refer to the Bessel table. When the beta value is increased by n times, we can calculate the bandwidth by using 2 times n times Fm. Okay, so let's do the example here. This example, so this example also has this is also one of the favorite question in the final exam. Okay, where we ask about both of this method to use the heterodyning and also to use the multiplication process. Okay. Okay, so you see that you are given delta F 3 kilo, beta 0.3, FC is 500K. Okay, so this is the given in the input produced by the narrowband FM modulator. Okay, and then we want determine the carrier frequency and modulation properties. If we use first is if you use the heterodyning method. Okay, so if given the balanced modulator with a band pass filter tuned to the sum frequency, and given the local oscillator frequency is 99.5 megahertz. So you see that the band pass filter tuned to the sum frequency. Okay, so that means we have maybe we can list down all the parameters. Delta F in equal to 3 kilohertz. Given FC, FC is equal to 500. FC in kilohertz. Okay, FC is given, and then beta. Beta is given as 0.3. What else we can find from here? We can find the delta F. We can KF, VM, KF, delta F over FM. So we can find the FM value. This is all in, so FM in is equal to beta delta F beta in. So this is 3 kilo divide with 0.3. So we get here the value is how much? So we get 10. So FM is 10 kilohertz. Okay, and then what else? Okay, so let's say we up to here, so we get all the parameters. Bandwidth, actually bandwidth, you can also calculate bandwidth, but 0.3 is not available in the table. Maybe you can use a bandwidth by Carson. Since I cannot find 0.3 from the Bessel table, so I can use Carson. 2 times delta F in plus Fm in. Okay, so this is equal to delta F 3 plus 10, 3 plus 10, 13. Okay, so to 3 kilohertz plus Fm in is how much is this? Fm 10 kilohertz. So 13 times 2, 26 kilohertz. Okay, so so this is bandwidth in. So therefore, for the FC out, for the first question, so FC out is equal to FC in plus FRF. Okay, so this is equal to FRF is 99.5 plus 500, so we get 100.0 megahertz. Okay, 100 megahertz. So no need to put 0.0 lah, confusing. Okay, 100 megahertz. So 99.5 mega plus 500k, so you're gonna get 100 megahertz. Okay, what about delta F out? Delta F out is equal to delta F in, which is 3 kilohertz. Okay, beta out is equal to beta in, which is 0.3. Okay, Fm out is equal to Fm in, which is 10 kilohertz. Okay, and bandwidth out equal to bandwidth in, which is 26. Okay, 26 kilohertz. So this is if we use a heterodyning method. Okay, if we use a multiplication method with n equal to 10, that means FC out is equal to FC in multiplied with 10. So we get here is FC in 500, so becomes 500k multiplied with 10, so we get here 5 megahertz. Okay, and then what? Delta F out, delta F out is equal to delta F in multiplied with 10, so we're gonna get this equal to 3 kilo multiplied with 10, so we're gonna get this equal to 30 kilohertz. Okay, 30 kilohertz. Beta out is equal to beta in multiplied with 10, so we're gonna get this one equal to 3. Okay, 0.3 multiplied with 10, so we're gonna get 3. Okay, this is out. What about FM? Modulating signal not change. Equal to 10 kilohertz. Okay, what about bandwidth? So bandwidth out is equal to, so we use the new value, which is 2 times delta F out plus Fm out. So this is 2 times delta F out is 30 plus 10. So we get this, the 30 plus 10, 40 times 2, so 80 kilohertz. Okay. So this is if I'm using the bandwidth by Carson. Okay, bandwidth by Carson. So do you have question to ask about this? You can ask question. Do you have question? If you don't have questions, ada soalan nak tanya? Students, are you still there?
Yes, Doctor.
Yes, Doctor.
Okay, thank you for the response. So if you don't understand, you can ask. I will explain again. If you understand, that's good. Okay. So no question, I will move to the next. Yeah.
Doctor.
Ada soalan? You have question to ask?
Yeah, the last equation, 2. Can you repeat, please?
Which one?
Question 2.
Question 2. So question 2, it is said that what happened to the output parameters if we use the multiplication method? Multiplication methods here, it is given the multiplier value n equal to 10. That means if we refer to the this picture, okay, all parameters will be multiplied by n factor. Okay, the multiplication factor is given as 10. So we need to multiply all parameters by 10, the factor, except for the modulating signal frequency, which is not changed. Okay, so what happened is that first I find the carrier frequency, which increased by factor of 10. So 500 kilohertz multiplied with 10 is gonna be 5 megahertz. And then delta F out is equal to 10 times delta F in. Delta F in is 3 kilohertz multiplied with 10, so we're gonna get 30 kilohertz. Okay, and then what? Modulation index beta out. Okay, so this is beta out is equal to 10 times beta in. Okay, so we get 0.3 multiplied with 10. So here is a beta in is a 0.3. So 0.3 multiplied with 10, it is equal to 3. And then modulating signal frequency Fm out is equal to Fm in, no change, which is 10 kilohertz. Okay, if you see from here, only the modulating signal frequency does not change in the multiplication process. Okay, and then what? Bandwidth. Bandwidth out is equal to 2 times delta F out plus Fm out. So I'm using the Carson's. So since at the beginning I'm using Carson, so I'm also going to calculate using Carson. Okay. If I want to use Bessel, you can also use Bessel, bandwidth by Bessel to compare. You can use Bessel. I use Carson because the value is very small. Beta value is very small, 0.3. It is not stated in the Bessel table, so I use Carson. Okay, saya gunakan Carson kerana 0.3 tidak ada dalam Bessel table. Yang dalam nota ini, the table in your notes does not contain a modulation index beta equal to 0.3. So that's why I use the bandwidth by Carson. So So if you see from here, bandwidth out is equal to 2 times delta F out plus Fm out. So 30 kilohertz plus 10 kilohertz. So and then multiplied with 2. So we're gonna get 80 kilohertz. Okay. So this 80 kilohertz is larger than the bandwidth in. Okay. So the bandwidth is actually depending on the value of beta. The higher the beta, the higher would be the bandwidth. Okay. So you understand now? You have more question to ask?
Yes, I understand, Dr. Thank you so much.
Okay. Any more question? No more question. Okay. FM demodulation. Okay. FM demodulation. So this is how we want to do the demodulation process. So demodulation process happens by changing the frequency variation to become amplitude variation at the output. So now we want to do reverse process. Okay, so you see that the frequency variation, okay, frequency variation of the carrier, because the input now is FM. Okay, we receive the input signal as the frequency modulation, angle modulation signal. We need to change it to a amplitude variation output. Okay, because the input is varies in terms of frequencies, so we need to change the frequency variation from the input to become amplitude variations. For example, here if you see the frequency response curve here, if the carrier move from rest to the maximum frequency, the output it will produce the output amplitude becomes maximum. If the carrier input move from rest to the minimum, the output frequency would be the output amplitude would be at maximum peak. Okay, maximum negative peak. So for example, here is negative Vm, over here is positive Vm, peak amplitude. Remember, demodulation process is the process to produce the original output message. We want to produce VMT. Okay, we want to produce VMT through the demodulation process. Okay. This one. So maybe we have a few times. Okay. So I will take a few minutes that we have now to explain to you about this process. Okay. So this is this has come out in the previous quiz question about this double conversion FM receiver. Okay. So you see that the word here is double conversion FM receiver because we down convert the frequency 2 times. Okay, that's why we have the first mixer and we have the second mixer, and we have 2 IF. Okay, we have 2 IF. Okay, so IF frequencies, remember in AM, the center of IF is 455 kilohertz. But in angle modulation, we have 2 different kind of IF. Because the frequency is not directly changed from RF to IF, we need to down convert 2 times. So what happened? Okay, let me explain to you. So for example, FM, so we receive from 88 megahertz until 108 megahertz. Okay, receive from the antenna. So for example, I want to listen to a radio station. Okay, for example, I want to listen to a radio station, Era FM, for example. Okay, Era FM is 104.5 megahertz, for example. Okay, That means the pre-selector will tune at the center frequency of 104.5 megahertz. Okay, and then what? So and then it will be amplified, the signal will be amplified and then put inside the mixer, the first mixer, which will mix with the first oscillator. So what happened here is the down conversion. Remember the mixer converter, we have the we have the what we call as the high side injection and low side injection. Okay, remember that FIF is equal to FLO minus FRF. This is for the high side injection. FIF is equal to FLO FRF. Wait, if we use a low side injection, that means FRF minus FLO. This is if we use a low side injection. Okay. Normally we use a high side injection most of the time in practical cases. Okay, and remember for the first IF, by standard it is equal to 10.7 megahertz. The center of the first IF is 10.7 megahertz, and then the second IF is equal to 455 kilohertz. Okay, I'm talking about the center frequency. So 455, just like in the AM, okay, just like in the AM that we have learned previously. Okay, so what happened to the so that means this is by standard, this is by standard. That means the first IF by standard, the center frequency is 10.7 megahertz. Second IF is equal to 455 kilohertz. Okay. So now we want to find what is the if it is put inside the mixer. Mixer will produce, remember mixer will produce FLSB and also FUSB. Okay, so FLSB is equal to FLO minus the FRF. Okay, which is equal to FIF. Okay, which is equal to FIF. Okay, and FUSB is equal to FLO plus FRF. Okay, this is the multiplication process in first mixer. Remember, mixer multiplied, so it produced upper and lower. Okay, so now the issue is what is the suitable FLO? What is a suitable FLO? So FLO is equal to, if I use a high side injection, okay, if I use a high side injection, it will be FRF plus FIF1. Okay, if I want to use a high side injection, that means my local oscillator must be higher than the input. Okay, so that means 104.5, this is the radio station that I want to listen. Okay, megahertz plus 10.7 of the first IF. So this is equal to 115.2 megahertz. So I need to use local oscillator frequency of this value if I want to use a high side injection. Okay, so this is a high side injection. Okay, and if I want to use a low side injection, that means my FLO is smaller than the FRF. Okay, which is FRF minus FIF1. Okay, that means it will be 104.5 megahertz, the channel that I want to listen, minus 10.7 megahertz. Okay, so this is become 93.8 megahertz. So this is the local oscillator frequency, the first local oscillator frequency. Okay, if I want to use low side injection. Okay, so let's say I use a high side injection. Okay, let's say I use a high side injection. Okay, so I use a 115 okay, so let's say I use a high side injection. Okay, so that means the FUSB, the upper side band produced by the mixer. Remember, the mixer will produce FLSB, FUSB, okay, and then FIF. Okay, at least there are three components, upper, lower, and the center. Okay, so I know that the FLSB would be the IF, the first IF, which is 10.7 megahertz. So the upper frequency that I can find, FUSB, for the first mixer, okay, which is FLO plus RF, okay, plus FRF. So this is equal to 115.2 megahertz plus the frequency channel that I want to listen, 104.5 megahertz. So this is become 219.7 megahertz. Okay, the FLSB, okay, FLSB is equal to 10.7 megahertz. 10.7 because this is the IF. Okay, so this band pass filter will select only the desired frequency band. Okay, it will allow the center frequency 10.7 megahertz towards the second mixer. Okay, so what happened at the second mixer? Okay, so second mixer, again, what happened here, we don't know how much is a second local oscillator that I need, but I know that the second IF that I should produce is 455. Okay, so what happened? So the lower frequency band, FLSB, produced by the mixer is actually equal to FIF2, okay, which is FLO minus FIF1, so it becomes FIF2. Okay, while the FUSB is equal to FLO2 plus FIF1. Okay, so FLO2, if I want to use a high side injection, okay, so this is FLSB and FUSB is the frequencies produced by the mixer. Now I want to know how much is the second local oscillator frequency that I need. Okay, so if I want to use a high side injection, okay, if I want to use a high side injection, that means FLO2 is equal to FIF1 plus FIF2. Okay, so this is equal to 10.7 megahertz plus 455 kilohertz. So this will produce 11.155 megahertz. So I need local oscillator. If I use a high side injection, I need to use 11.155 megahertz. But if I want to use a low side injection, okay, if I want to use a low side injection, that means FLO2 is equal to FIF1 minus FIF2. So I'm gonna produce 10.7 mega minus 455 kilohertz. It equal to 21.855 it becomes a 10.245 sila Sorry, I'm gonna take a few minutes of your time to complete this So this is 10.245 megahertz This is if I use a low side injection. That means the local oscillator frequency is lower than the input. Okay, so assuming that I'm using the high side injection, okay, assuming that I'm using the high side injection, now the issue is I want to know how much is the FUSB, FLSB, and then FIF. Okay, I know that FIF gonna be 455. I can sorry, the FLSB is a 455. Okay, so maybe I make confused here, so I delete this one. Let's assume that it produce 2. Katalah dia menghasilkan 2 frekuensi pada output. Mixer ini menghasilkan 2, upper and lower. So I know that the lower sideband is the second FIF, and I want to know how much is the upper sideband frequency. Okay, the lower sideband produced by the mixer is equal to the second intermediate frequency. So if I use a high side injection, I want to find the FUSB. Okay, this is equal to FLO2 2 plus FIF1. Dia tambah tolak just a plus and minus actually Remember, mixer produce upper and lower frequency. Okay, so this is if I use a high side injection, that means this is a 11 point from this value 11.155 mega plus the first IF is 10.7 megahertz. So this is become 21.855 megahertz. Okay, so this is if I use a high side injection. If I use a low side injection, I gonna produce FUSB equal to FLO2 plus FIF1. So I gonna produce, this is equal to 10.245 mega plus plus with I use this one if I use a low side injection plus 10.7 mega. So I'm gonna produce upper sideband equal to 20.945. 20.945 megahertz at 20.945 megahertz. Okay, sorry. So we have the flexibility to use a high side injection or low side injection. So now the issue is I want to find the upper sideband. I already know the lower sideband frequency produced by the mixer, which is equal to the intermediate frequency. Okay, so the second intermediate frequency, which is the FLSB, so the band pass filter select the low frequency. Okay, band pass filter select the low frequency, which is the FLSB. So FLSB is equal to the intermediate frequency. So the second intermediate frequency goes to the IF amplifier. Okay, increase the amplitude, and then we filter out the frequencies. Okay, limiter here means that we limit the amplitude. We do the demodulation process. Okay, from 455 kilohertz of center IF to become FM. Okay, de-emphasis, we reduce the amplitude since we increase at the transmitter, and then amplify the output, and then goes to the speaker. We get the VMT, which is era FM. So in FM double conversion, actually we reduce the we down convert the frequency for about 2 times. Okay, so this is the double conversion FM. Okay, so I think you already tired, so maybe I take 12 minutes, sorry about that. So that's all for today. Okay, so this has been asked in the quiz, just a objective question. The objective question asks about the output frequency at each mixer. So the mixer frequency is plus and minus from the input, because we have 2 input, so you just need to plus and minus. Plus you get the upper sideband, minus you get the lower sideband. Okay, so that's all for today. You can take the attendance, and then you can go out. So that sorry that I take a few minutes of your time, 13 minutes, sorry about that. So you can open your QR code reader. Okay, see you again next week.
Okay, thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Okay,
Thank you,
welcome.
Doctor.
Welcome.
Thank you, Doctor.
Okay, welcome.
Thank you,
Thank you,
Doctor.
Doctor.
Okay, welcome.
Doktor, saya
Ya.
tak boleh scan.
Siapa nama?
Muhammad Hamsyari.
Okay, done.
Nombor 15, Doktor.
Doktor.
Muhammad Amir Amri Adam.
Okay.
Ya.
Okay, dah.
Thank you, Doktor.
Okay, welcome. Any more?
Doctor, I cannot scan.
What's your name?
Muhammad Jokri.
Muhammad Jokri. Okay.
Alright, thank you, Doctor.
Okay, welcome. Any more?
Doktor,
Ya.
saya tadi nak scan tapi tak boleh keluar. Tapi saya tengok kat situ, nama saya dah titik.
Siapa nama?
Izzat Izzani.
Ada ni? Ni-
Itu yang saya confused tu.
Tak,
Saya scan
Tak,
tak lepas.
maknanya kamu dapat scan lah. Berjaya scan lah. Berjaya
Okay.
scan. Okay?
Terima kasih doktor.
Okay, welcome. Who else?
Thank you doktor.
Okay, welcome. So, Aiman dengan Amin tak ada?
Doktor,
Daniel Putra. Ya?
doktor,
Ya.
saya nak tanya berkaitan
Amin ada ni? Ya. Silakan.
tentang assignment tu due date 21/5 ni
Ya. Macam mana nak extend ke masa?
boleh extend ke?
Oh, boleh. Tak ada masalah.
Boleh.
Boleh.
Bila berapa lama yang doktor bagi extend?
1 minggu ke? Okey.
1 minggu
Boleh.
Okey, boleh. Saya cuba dulu.
Aha.
Kalau ada apa-apa pertanyaan, saya direct contact
Sebab
doktor.
saya nak masuk yang task number 2 belum masuk lagi ni.
Betul. Belum masuk lagi.
So,
Okeylah, kalau macam tu extend seminggu.
Boleh?
21 Mei nanti, tambah lagi 7 hari lah.
28. Okey.
Okey, boleh.
So dah start buat ke langsung tak buat?
Baru survey
Ah.
nak fahamkan dahulu.
Sepatutnya dah kena buat sebahagian lah. Sepatutnya kamu dah ni. Okey lah, tak saya tambah seminggu lah. Hopefully dia boleh siap. Okey?
Okey. Boleh doktor. Terima kasih doktor.
Okay, sama. Okey.
Doktor, tadi saya disconnected.
Siapa?
Ada nama saya dah Muhammad Amin.
Amin dah tadi. Alif Aiman dia tak ada.
Okey doktor, thank you.
Okey.